We looked at a number of series so far, most recently infinite geometric series. Today, I want to discuss a power series, which is simply an infinite series that takes on the following form here. So let me just zoom in on this so you can get a sense of what a power series looks like. So a power series is a series that takes on this form. So if we think now what these series would look like, we would have something like a sub 0 times x minus c to the 0 power plus a sub 1 times x minus c to the 1 power. And you see where this is going. And this is an infinite series, so I'm just going to indicate that right there. So this is an infinite power series. And so the first thing you should notice about this that makes it unique is that this is a series where it consists of variables instead of just numeric values, right? Instead of just looking at numbers, we're now looking at variables or series composed of variables. And I want to start by looking at a specific type of power series first to help develop our understanding of it, because we're going to spend quite a bit of time on power series in this course. So it's probably a good idea to start with a more approachable series, something that's a little bit easier for us to digest. Specifically, let's look at a geometric power series. So what is a geometric power series? A geometric power series is simply a power series where all the coefficients are constants. In both power series and geometric series, we notice that we're multiplying by the same thing over and over again. In the power series above, we were multiplying by x minus c. We would say that that could be our common ratio. And so the only thing that makes a geometric power series unique or distinct from just all power series is that we do have a common coefficient. We have the same coefficient over and over again. So let's look at this particular geometric power series that we have here. So a sub n is x to the n power, and we would write 1, the next term would be x, the next term after that would be x squared, and so on and so forth. Here we notice that our coefficients in this case are all 1, so they're all constant. Well, what do we know about geometric series? We know that if they converge, or I should say they will converge, or in other words, they will have a finite sum if the absolute value of its common ratio is less than 1. So in other words, we know that a geometric series will have a sum, right? And here's the sum formula that we saw in the last video. They will have a sum if the common ratio, or the absolute value of the common ratio, is less than 1. Well, if you look at this power series here, what is our common ratio again? What are we multiplying by every single time? Our common ratio is x. That's what we're multiplying each term by to get the next term. So we could say here that our sum, if it exists, our finite value, if we do have a finite sum, it would be, in this case, 1, which is our first term, over 1 minus x. And again, we will only have a finite sum if the absolute value of our common ratio, in this case, the absolute value of our common ratio, which is the absolute value of x, if that is less than 1. So here's something that's interesting about this. Before, we got to just look at a specific numeric value. In our previous geometric series, we just looked at, all right, what's the numeric value or common ratio that we're multiplying by every single time? In this case, we actually have a variable. We're saying for some value of x, depending on what that x value is, we may have a convergent geometric series or we may not. If our x value is within this interval, and remember, another way of writing the absolute value of x is less than 1 is to write it as this inequality. We say x is less than 1 or greater than negative 1. So we're saying if our x value is within this interval here, then our geometric series converges. In other words, its sum, the sum of this geometric series, will be exactly equal to this if our x value falls within this interval here. And this interval that we have written out, we call this our interval of convergence. And you'll often see me say, or hear me write, or watch me say IOC. Hear me write. That still doesn't make sense. Hear me say or watch me write interval of convergence, or IOC for short. There we go. I think I finally got it. All right. So let's actually look at the graph now, because I think that'll really drive in the implications and consequences of what we're discussing right now. So let's go ahead and go back to our Desmos here. Okay. And what we have here is I've just graphed out our series in summation form. And right now it just looks like a line because we're stopping at n is equal to 1. But what I want you to see here is what happens to this as we approach infinity. Right now we're just at n is equal to, or in this case as was written on the slider, 36, 38, 39, and so on. And you're going to see that the left tail of this is just going to oscillate back and forth, going up and down. And that's really just because n represents the degree of this function, right? When n is an odd number, then we've got the left n falling and the right n rising. When n is an even, let me try to see if we can stop it on even number. Nope, can't do it. There we go. When n is an even number, then we have both ends of the graph going up, which is just why it's oscillating. And because we have a positive coefficient, that's why the right side doesn't ever actually move. But let's start back from here, just so you can kind of see what's going on here, right? We're going to see that after a while, with n approaching infinity, and I'm really even stopping well short of that, it's going to, after a while, start to remain pretty constant. Now, what I want to do is I want to compare this series now, this infinite series, which I'm representing as a finite series, but this infinite series to its sum. And what did we say its sum was? We said it's simply a over 1 minus r, or in this case, 1 over 1 minus x. And something that I want to highlight for you, I just wanted you to kind of observe what's happening here and compare. And maybe let me just kind of go back here and then just go even closer just so you can get a sense of that. What are we noticing there? After a while, and it doesn't take very long, in fact, it's probably maybe after the first 5 or 6 terms or so, we start to see that this series looks really, really, really close to our sum. And in fact, what did we say our interval of convergence was? We said from -1 to 1. So let's zoom in there really close to that. So between -1 and 1, and we go back here, what are we noticing? That this sum and that series are practically indistinguishable from one another. And as we get closer and closer to infinity, you won't even be able to tell the difference between the two. And this is so important because this is our first jump into the idea that an infinite polynomial series can be exactly equal to a more complicated function. That is to say that we can use an infinite power series to represent a function. That this geometric series that we have right now, x to the n, can be expressed or as this following function over its interval of convergence. And this has a lot of applications in engineering or finance. The idea that you could take a series and represent it using a simpler polynomial function. Or the other way around, to take a complicated function and to look at its representative infinite power series and just look at the first couple of terms of that power series to get a sense of what that more complicated function is doing. I'm getting way ahead of myself right now, and this is what we're going to spend the next, however many number of weeks discussing, but this is a really important idea here. So going back to the sense that we can use a geometric series or a power series and represent it by its function, which is simply the sum of that series, which again only occurs over its interval of convergence. I want to look now at a geometric power series centered at some other value c. And this is simply when we have a power series that's centered at some value other than 0. So all really just the main difference between what I had written up here and what you're seeing here back here was here we had a geometric power series. The first example I gave was one that wasn't centered at 0. or excuse me, the first one I gave was centered at 0, but you may have some other power series that are not centered at 0. And all that really just means is it's like a horizontal shift, if you will, because that C value represents the center of your interval of convergence, right? If you think back to this first interval of convergence we looked at, what's the exact center of this interval? Well, it's 0, because this geometric power series was centered at 0. If you have a power series that is not centered at 0 or at some other value of C, that's going to represent like the middle point of your interval of convergence. It's going to be your center. That's why we call it a center. So let's look at this particular geometric power series and just go through a couple of quick questions. So first off, what type of series is this? Well, it's clearly a geometric series. What is our R value here? Our R value here, what we're multiplying by, our common ratio, is x minus c. What's our first term? So we would say a sub 0, right? It's the first term in our series. It would just be equal to a. And can we find the sum of this series? Well, we know that if this series converges, the sum of this series is going to be our first term, a, over 1 minus r. And what's our r value here? It's x minus c. Okay, being careful with our parentheses here. So that's our sum. What is another way of expressing that? Another way of expressing that is simply for us to subtract or distribute that negative, I should say, and write this as a over 1 plus c minus x. And all I've done there is just distribute that negative. So to continue on this train, will this series converge for all values of x? Well, it will converge. What do we know about geometric series? They will converge when our common ratio, or when the absolute value of our common ratio is less than 1, right? And another way of expressing this, again, is to say the following, is to express this as our interval of convergence. Just write this as this compound inequality, right? When x minus c is less than 1 or greater than negative 1. And again, if I want to use inverse operations just to isolate our x value, we could say when x is less than c plus 1, or when it's greater than c minus 1, which is our interval of convergence here, okay? So we're going to go through some examples right now where we look at some power series, and we're going to show the terms, and then also practice finding its interval of convergence. I just want to note that I do have this part in the notes where it gives you another way of thinking about expressing these power series using different functions. I'm going to gloss over this right now. I'm just going to skip over it actually. If you are interested in this, check my scan notes and you can see my breakdown here, but at the fear of confusing you even more, I'm just going to pass over this for now and just get right into some of these problems. All right, so we're doing a couple things here. Let's look at this first example, and let's find a power series for this function. So what we're going to do is given this function here, we are going to express a power series that represents this function. So let's take a look at this here. We can say, all right, it looks like it's following the sum formula. So we can say that for this geometric series, that our first term, a, is equal to 1, and our common ratio, r, is this value here. So we can say r is equal to 5x. So we're going to express this function as a power series. We're going to say f of x, this function that we're seeing here, basic rational function that we've seen many times, can be represented by the following power series. The first term, 1, and then multiply every term by the common ratio, plus 5x, plus 5x, being careful with our parentheses, squared, plus 5x cubed, and so on, okay? And actually, I've kind of jumped to part B already. I've shown the first 4 terms of the power series. What I do need to do now is I need to express the general term. So what is our a sub n, if you will? So I'm going to just kind of change this back to a and b, because we're doing both parts right now, a and b. So what is our a sub n? Well, our a sub n is simply 5x raised to the n powered. This, again, is our a sub n, our general term. Okay? So now let's express this series in sigma notation. So once you have your general term, this is pretty easy. So we're going to say, all right, it's the summation of, starting with n is equal to 0. And I don't really care too much whether you start with n is equal to 0 or n is equal to 1. That's obviously going to change your general term. Doesn't matter too much to me as long as it still works with the series. But I'm going to just start with 0 since our first term was 1 here. So we're going to say this is our a times our common ratio, which is 5x raised to the n power. All right. Now finally, now that we've been able to express this function in terms of its power series, let's find its interval of convergence. Well, the IOC, or its interval of convergence, is simply our common ratio, 5x, when we say the absolute value of that is less than 1, or when it's less than 1 or greater than negative 1. So we can then say x is less than 1 over 5, but greater than negative 1/5. So there's our interval of convergence. So we can say that this power series will converge when x is less than 1/5 or when it's greater than negative 1/5. Okay, let me do one more with you and then give you some time to try some of the practice problems on the back. Let's try this series now. So here, before we go ahead and start determining our common ratio, it might be a good idea to remember to find a way to express this as a over 1 minus r. And since we have a 2 plus x there, we have to do a little bit of rewriting, which isn't too bad. We're just going to rewrite this as 1 minus 1 minus x. And that's what allows us to write this in this form here. So we can then say the following. We can say, all right, this is a geometric series where our first term, a is equal to 1, and our common ratio is negative 1 minus x. Okay, so writing this here, we can say our series, again, let's make this our a and b, f of x is equal to, let's write the first 4 terms. We've got 1 plus negative 1 minus x plus negative 1 minus x squared plus, and I'll continue this on the next line, negative 1 minus x cubed. And we're going to indicate that there are an infinite number of terms, and now we can write our general term as negative 1 minus x to the n. And we always want to write those dots at the end of that to indicate that it is infinite. Part C, we're going to write that now in summation notation or sigma notation, starting with n is equal to 0 to infinity. Our first term is 1. Our common ratio is negative 1 minus x to the n. And then finally, for part D, our interval of convergence, we can then say, well, when this is less than 1 or greater than negative 1. We should simplify this here. So this is going to be negative x is less than 2, greater than 0. And we're going to divide everything by negative 1 now. So x, and be careful now to switch the signs. That's still going to be 0. And we know it's bad practice to write the inequality that way. So we're going to just clean it up by writing x is less than 0, but greater than negative 2. And there's our interval of convergence. Okay? So hopefully this helps make sense of what makes something a power series, what is a geometric power series, and the really important connection between a geometric power series and its representative function over its interval of convergence.